Okay, so let's say we have this, this graph with a line through it, and the line is going to, in this case, go through the origin, but it doesn't really have to. What we want to do first is look at how slanted the line is. And so one of the ways to think about the slant of the line is think about it as a rate of change. So as x changes, then y will change as well. And in this case, with this graph, as x increases, y increases. And so we'll look at those two differences, and we'll call the ratio between how much it goes up to how much it goes across is, we'll call that the slope. And traditionally we use m to represent the slope. And so the change in y divided by the change in x is just going to be y2 minus y1. And so think of this as the rise over the run that for some reason is easily memorized. And we can calculate what that slope is numerically. So if we think about what these numbers are when we have different values in there, if there's a large change in y with a small change in x, so the line has a very strong slant like this, we say the slope is great, so you'd expect a large number, large positive number if that's the case. And then as we start to flatten out, as there's almost no change in y for a large change in x, we'd say there was a small slope. So this definition of the slope does give us a numerical value which corresponds to what, how strongly the line is sloped. Now if the line goes from the upper left to the lower right, we say it has a negative slope, and in fact we'll find that numerically holds true because as we increase x, that's positive, y will go down and that'll be negative, and so we'll have a negative value, that it becomes more and more negative, a smaller and smaller number but a larger magnitude number as the line decreases. Okay, so let me give a particular example here. Let's say we have 2 points, and notice this line doesn't go through the origin. It really doesn't matter where the line goes through the axes, but if we have those 2 points, we'll use our formula for the slope, and you see we take the difference in the y's, 4 minus 2, and then divide it by the difference in the x's, 5 minus 1. Now I called this point 2 and this point 1 corresponds to y2 and y1. It really doesn't matter which one is the first point and which one's the second point, because if you swap these around, notice you'll have 2 minus 4 over 1 minus 5, and so you'll have a negative over negative and we'll get positive. So long as you keep the correspondence correct, where the first numbers are from one point and the last numbers are from the other point, then you'll get the right magnitude or the right numeric answer to calculating the slope. So in this case, we have 2 over 4 is 1/2. Okay, so we'll do just another example here. We get a line with a steep slant. We're going to expect a negative number out of here. So if I choose any 2 points along this line, and I'll just take 2 convenient points, which is -2 and 6 and 2 and -4, calculate our slope, and we have -4 minus 6 over 2 minus a -2, and so that works out to be then -10 over 4, so our slope is -5/2. Now, this is negative in the numerator. Had you used the points in a different order, we would have had the negative in the denominator, and that's both the same if we put the negative out front. So what you want to do is reduce this to lowest terms. So 10/4, -10/4 is a correct answer numerically, but the proper answer would be -5/2. Now, if you have a whole number, if this instead turns out from 5/2, let's say if that was just something like -2 over 1, feel free to state the slope as an integer. You don't have to put it as a ratio. Of course, any integer can be expressed as a ratio by just putting it over 1. So numerically, just a simplified fraction is really all you need. Okay, so that leads us to the first form of an equation of a line, and this one's called slope-intercept form because what we're going to use is the intercept to complete the equation. So the general form of this line is going to be y equals mx plus b. Okay, so whenever you see that, this is going to be the slope, this is the intercept. Okay, so the slope is m, b is the intercept. And so the way this works out is when you think about what happens with this b, when you have x equals 0, then mx equals 0, and so what you have just is y equals b, and so that tells you when x is 0, where does it cross through the y-axis? And that's just the numerical b. So, of course, if the slope is positive, then y is increasing as x increases. If m is 0, we have 0 or no slope, so that means we have a horizontal line. And then if it's negative, we have y decreasing as x increases. And of course, if it's undefined, that means we have division by 0. What we have is a vertical line. And so let me draw a little sketch on the side here to show a vertical line and how we get that. So if we have, let's say, at this point, let's say 2, we have a vertical line through here. If this is 1 and let's say this is 3, we'll have 2 points. This is going to be 2, 1, and this is going to be 2, 3, those 2 points. So if we calculate the slope there, we get 3 minus 1 over 2 minus 2, which is going to be 2 over 0. So we have division by 0, and so the slope here is undefined. And that's the only way we need to describe it, is just to use undefined for the slope. Now, similarly, if we have a horizontal line, I'll write this in a different color. So we still have this point 2, 1, but let's say out by, let's say 4 or so, this will still be 4, 1. We have our slope is going to be the difference in the y's divided by the difference in the x's, which is 4 minus 2. And so we have 0 over 2, which is just 0. So 0 slope is horizontal, and undefined slope is a vertical line. Everything else has a numeric value to it. Okay, so let's use an example here and figure out what this graph looks like. So we look at the equation y equals 2x plus 1. The slope, which is the m value, is 2. The y-intercept is 1. And so if we want to graph something like this, one of the easiest ways to do this is just to start at the intercept, which is going to be 1. And then we're going to count off the slope by using the rise over run concept and just say, okay, we're going up 2 and over 1, and we can do that any number of times, and we'll get our line. Now with a graph, all we need is really, with a graph for a line, all we need is 2 points. So if we draw this carefully enough, we can just use the straight edge to get the rest of the line, or you can restate your slope in terms of a larger, or a ratio with larger numbers, let's say 4 over 2 or 6 over 3, and then we can count out them and get 2 points that are further apart. And the further apart you have your points, the more accurately you'll draw your line. Okay, so 2 points are sufficient. Okay, so that's what I was just saying about use a larger integers in your ratio, and you can go 4 over 2 and you get that more extreme value. Okay, so let's talk a little bit more about slopes. And let's say we have these two lines. Now, the two lines here are parallel. And what parallel means is that they don't intersect anywhere. They go on indefinitely, and there'll be no time that they intersect. So that means any change that we have on one line, we're going to see the same change on the other. So we can say that by saying, okay, our slopes are going to be equal. And if I count out these on my graph, I have my equations of the line are basically, I can calculate what the slope is by saying, oh, my rise is 3 over my run of 4, so that's 3/4. Same thing here, my rise is 3 over a run of 4. Now look at the intercepts, and the b value here is 1, and the b value here is -1. So our equations look similar, but the intercepts are different. Okay, so let's say we don't believe ourselves and saying, okay, there must be some place where these lines intersect. So the lines intersect when both the x and the y values are the same for both lines. So let's see if we can actually compute what the intersection point would be. If I'm going to say this is line 1 and this is line 2, so I'm going to label x and y 1 and 2. If the two y's have to be the same where it's intersected, then what I can do is I can set these two equations together and see, okay, what's my x value? Where are they going to intersect? And actually, when you have 3/4 x plus 1 equals 3/4 x2 minus 1, there's no solution to this, because if we subtract, if we have the x's equal, if we subtract 3/4 x from both sides, we get 1 equals -1, and of course there's no solution. So we know that parallel lines don't intersect, that's by definition, but a little bit more from a practical standpoint, if we try and compute the intersection of the two lines, it doesn't exist. We get no solution between these two lines. Okay, so now let's talk about perpendicular lines. And what I want to do is, there's a formula that, there's a relationship between the two slopes on perpendicular lines, and our textbook just kind of pulls it out of the air that says one is the negative reciprocal of the other. But let me see if I can justify that visually for you. Let's say I have a piece of cardboard or just some shape, 6 wide, 3 high. Now I'm going to cut it on the diagonal. This is a 90-degree angle. So what I'm going to do is I'm going to take this top piece and open it up. So what I have is this right here. Okay, so what I've done by opening it up, this side here is going to drop here, and you can see I'm rotating this 90 degrees. So all the angles will increase by 90 degrees. And so this is now straight across, so this is 180 degrees, and I know the sum of these two angles is 90, so the angle in between those two lines I know is 90 degrees. So what I have here are perpendicular lines. That's what that means, that the lines intersect at 90 degrees. So let's calculate the slopes of these two. And so the slope of this line here in the yellow, we'll take that as the rise, which is actually, I'm going to go from this point down to this point, so I'm actually dropping 3 while I'm increasing 6. So I got a -3/6, or I'll call that -1/2. So this slope is -1/2. Everybody see how I got that? It's just decreasing by 1 unit for every 2 units we go over. Now if I look at the other line here, this slope, this one is going to go up 6 and down 3, or over 3 and up 6. So my slope here is going to be 2 over 1. And notice the relationship between the -1/2 and the 2 over 1. And so we have this relationship in perpendicular lines that says that two lines are perpendicular when the slope of one is the negative reciprocal of the other. So here we can state the slope as 2 if we want, or 2 over 1. And so if we take the reciprocal of this and make it negative, we get -1/2. And so there's the relationship where we can tell that perpendicular lines, indeed, the slopes have that relationship. Now I just arbitrarily chose 6 and 3. You can do this with any any two numbers, imagine this one being, let's say, a 2 and this one being a 7. So we have negative 2/7, and then this will be positive 7/2. And so, it generalizes very easily. And in fact, if you just want to do it with variables, you can. Okay, any questions on that? It amazes me that our book doesn't actually explain that. It just kind of throws out this relationship. But here it is, and hopefully that doesn't look as mysterious as just a formula thrown at you. Now, one of the things that I mentioned at the beginning is that the slope can be thought of as a rate of change. So what we want to do is think about this. If we say the y changes over the x change, think of that as a over b. Basically, for every increase in b units, there's an increase of a units. Okay, so think about maybe the slope of a line. If you're driving a steady speed, that the slope of the line is your speed. And so for every, in the denominator, for every increase in time, so for every hour, you're going to go a certain number of miles when you have a miles per hour kind of statement in your, as your slope. Now, when you get to calculus, this is going to be a crucially important concept, that slopes are rates of changes, or a way to describe a rate of change in a function. And here we're dealing with lines, but when you get into calculus, you'll be dealing with slopes of curves, things that change. And that conceptually isn't too hard. It's like driving in a car and your speed changes. You'll go a different amount of distance depending on the different speeds that you go. And so we're going to be looking at, ultimately when you get to calculus, you're going to be looking at slopes of curves as being the line, the same as the line tangent to the slope. So this particular definition of a slope is going to be really important all through calculus. Okay, so here's an example. At 1 p.m. I'm going 12 miles from home. At 4 p.m. I'm going 36 miles from home. How fast am I going? Okay, so here's a change in time and a change in distance. We can look at those things as being coordinate pairs. So at my time and my distance, I have 2 points, 1, 2, and 4, or 1, 12, and 4, 36. And so if I compute the slope between the two of those by taking the difference in the y's divided by the difference in the x's, I know that I'm traveling 8 miles per hour, if those are my 2 data points, and the assumption is that I'm going a steady speed, a uniform speed. Okay, so let's look at now equations of lines. There's going to be more than one way to look at the equations of lines, and so let's take a look at an alternative here. So if we have the slope of a line constant, it doesn't change. That's what makes it a line, and we have the slope defined as the ratio of the y's and x's. I can say, okay, for any 2 points on this line that I choose, I have this slope. And so instead of maybe making a particular point, let me leave the subscript off of the x and the y. So long as x and y are along the line, we can use any x and get to that y, and it'll have the same slope. Okay, so all I've done is I've removed the 2 as a subscript and saying any. Now, this m, of course, is this definition. So let's say I'm going to do a little manipulation here, and I'm multiplying both sides by x minus x1. Okay, and so I'm going to multiply it, so I just get y minus y1 here. And on this side, I have m times x minus x1. What I end up with here is a perfectly good equation of a line, right? y1 is known, my slope is known because I've determined that from 2 points. x1 is known, and so I have a relationship between x and y that I can get just by using that little manipulation there. So let's put that into practice. So let's say we want to find the equation of the line through 1, 2, and 2, 5, well, the first thing we do is we calculate the slope. So that's 5 minus 2 over 2 minus 1, and we get 3. And then, excuse me, we put this in the form where we just choose one of the points, and it doesn't matter which point we choose so long as the x and the y correspond to each other. So I'm going to use that first point of 2 and 1, and I stick it in there. There's my equation of the line. And so if I want to simplify that, I can extend the 3. So remember, these parentheses here are really important. So I'm going to say 3x minus 3 instead of 3 times the quantity of x minus 1. And then I'm going to add 2 to both sides, and the equation of the line that I have is y equals 3x minus 1. So that's, this form of the equation is called the point slope version, because we have a point and a slope that tells us what the equation of the line is. Now, one of the things you can do is go back and check your points to put in here to make sure you have the right line. So if you put a 1 in here, you get 3 times 1 is 3 minus 2, or minus 1 is 2, and so that corresponds to this point. If I put a 2 in here, I have 3 times 2 is 6, minus 1 is 5, so that point works also as well. So it's very easy to check if you have the right line. You just put one or both of the points in the equation, and it should work out. So we call that the point slope form. And so we just use our slope and then one of the points to get to the equation. Some textbooks will actually write, instead of m here, they'll write y2 minus y1 over x2 minus x1, and it's the same thing, it just looks a little bit more complicated. I think it's a little easier to remember this. So why don't you try this? Here's, find the equation of the line containing these 2 points, 6, 6, and negative 3 and 0. Okay, somebody walk me through on this one. How would you do that? Yes?
I saw for the slope, so 8 minus negative 1 over negative 2 minus 1.
Minus 1, okay.
And then I got 9 over negative 3, which is negative 3. And then I plugged it in, so I got y minus negative 1 equals negative 3 times x minus 1. So y plus 1 equals negative 3x plus 3. And subtract 1 from each side. And I got y equals negative 3 plus 2.
Plus 2. Good. Okay, and so this is exactly what you did. And you got that. Okay, so everybody good with that? Did I move over too fast? Okay, that's good. Okay, so let's look at a few more variations of these kinds of problems. Let's say we have a line and we want to find the line parallel to a particular equation through a specific point. Now, if you recall, parallel lines have the same slope. And so when we have this in slope-intercept form, we can identify the slope right away. And then all we need to do is use the point-slope form using this slope, and we'll get what we're looking for. So on this one, I identify my slope, and then I have my point, y minus 7 equals 5 times x minus 1, and then we can just simplify that and put that into slope-intercept form. Now, this is a perfectly good equation of a line, the point-slope form. This one is a little easier to graph and perhaps visualize. So even though these are two perfectly good forms, this one is really only used for determining what the equation of a line is. This is the typical way that you would represent the equation of a line. Okay, so if we check that, we can see that we have, we just put our point back into the equation and we can check to see that we have the proper line. Okay, so here's one now that's similar to it, but involves the concept of a perpendicular line. So let's say we want to find the equation of the line perpendicular through the line that goes through both of these points, and it goes through a point 2, 3. So here we don't have an equation of a line. We basically have 2 points and then a third point. And so we want to establish what's the line between those 2 points and what's the line that's perpendicular to those. So if we figure out the slope of the first line, we take the 2 points, 9 minus a negative 3, and a 7 minus a 1, and so we get 12 over 6, the slope is 2. Now we don't have to figure out, it's not asking for the complete equation through these 2 points. All we're really interested in is what's the slope. So here we have the slope, and we know that the perpendicular line is going to have a slope of the negative reciprocal, so it's negative 1 over 2. And we stick that point into our new equation and then simplify it. And so we get y equals negative 1/2 x plus 4. So if I graph this just to kind of visualize what we've done, if we have the points 1, negative 3, so that should put the first point right about here. Second point is 7, 9, and we'll draw a line through that, and then here's our point that we want to go through, which is 2, 3. And then when we actually find the equation of the line, we notice that the intercept is 4. So if I put a blue dot there, you can see that these 2 points belong on the same line. If I draw a line between the two of them, you'll see, at least it looks like, these are perpendicular. Okay, so we have, I want to describe several different linear equation forms. I talked about the slope-intercept form, that's the y equals mx plus b, that's the most common. We have the point-slope form, which is the y minus y1 equals m times x minus 1. This first one here is the standard form, and so this is just where you have coefficients x and y and c, and they all equal 0. So the standard form is perhaps the one that's used the least, but once we get into conic sections and things like that, we're going to have a standard form for parabolas, hyperbolas, and all that. And you'll see that it follows the same form where we put out all the different variables, x squared, y squared, x, y, x, and y, with coefficients, and put everything on one side equal to 0. Now there is one thing that is handy about the standard form, is that if you have a graph that the equation comes in standard form, let me write one like this, where we have 3x plus 4y minus 12 equals 0. If we have something like this, it graphs very, very quickly. What we want to do is we want to put the constant on the right side of the equation. So we have 3x plus 4y equals 12. And so very commonly you'll see this form of a line as well. You can recognize it as a line because you have both an x and y in there, and there's no exponents there. Okay, so the way that we can do this is that we look at our intercepts. And so what we do is the 2 points that we want are going to be when x is 0 and when y is 0. And so with this form, it's very quick to determine that. So when x is 0, this drops out. We have 4y equals 12, so we know y has to equal 3 in this case. And in this case, if y equals 0, this term drops out. We have 3x equals 12, so we know that x has to equal 12 divided by 3, which is 4. And so 0, 3 is 1 point. The other point is 4, 0. And that's this point. Then you draw a line through the two of them. And so this form graphs very, very quickly. And so what the goal here is when you're trying to do this is you want to use integer coefficients. So if these are fractions and everything, just get rid of the fraction by multiplying through by the denominators, and you'll get an equation like this that really, even without doing a lot of writing, you can figure out what the two intercepts are and get a graph. Okay, so what are you supposed to take away from this? Linear equations, one of the most important things you'll use in calculus, one of the most important tools. So what I'd like to do is summarize what I expect you to be able to do with lines. If I give you 2 points, you should be able to calculate what the slope is. You should be able to determine the equation of the line. If you're given a line and a point, you should be able to determine a parallel line through the point and also determine a perpendicular line through that point. And then for given a graph, you should be able to determine the equation of the line. And so when you're given a graph, what you do is you choose 2 convenient points. Now, it's you can read whatever is accurate, and oftentimes reading off the 2 intercept, the x and the y intercept, are the points to use. And also, making a graph, you have several ways of doing that. You can either do the way that I just showed you, or you can count off the slope, or perhaps in an equation like this, set x as 0, figure out what y is, and then set y to be equal 0, figure out what x is, and then you'll have the 2 intercepts as well. Okay, so I think that pretty much summarizes it. Now, also keep in mind, you should be able to write the equation of a vertical and a horizontal line. Now, with the horizontal line, you have the slope is 0, so all you're going to have, I'll just make a vertical and a horizontal line here. So a horizontal line has the equation y equals 3. So it doesn't matter what x is, y is always 3. Now, the vertical line doesn't have a slope, so m doesn't have a defined value. But what you do is you just set your value x equals 4, and so that will tell you what the vertical line is. So remember that it's just either y equals a constant or x equals a constant, and it's just a matter of getting the proper x and y, where y equals a constant is a horizontal line, x is a constant is a vertical line. Now, for one last application, here's a problem where you need to find what the rate structure is, and I'm going to assume here that this is a linear relationship. So think about those 5 things in getting a word problem. I'd like you to work on this, and then just before the end of class here, I guess we have 5 minutes or so, we'll take a look at what you got. Okay, so think of this as that 5-step process. So the first thing we want to do is gather our information. We can draw a diagram if we want. That really won't help us too much here. But what we may want to do is extract the data out of the question and say, okay, we have 295 corresponds to 1 point. So we're thinking in terms of a diagram that has the miles as the x-axis and the distance or the cost as the y-axis. So we have 2 data points, 295 and 150 and 85. And so then the first thing to do is we're going to calculate a slope. Now, I have pretty much suggested that we always look at defining our variables with and here I'm actually using one, but you can see here that I'm actually putting in the definition of what the slope is by doing a computation and say that's then 20 cents per mile. So there's my mileage rate, and it's labeled with units and everything, so it's basically, you know, already saying that that is a mileage rate. So then if we then look at, this is probably part of our model here, the equation, we'll stick one of the data points in here where we have y minus 95 equals 0.2 times x minus 200. If we multiply this out, 0.2 times 200 is 40, and so we will then simplify this. And so we get y equals 0.2x plus 55. So here's the rate structure then. So the rental car company charges 20 cents a mile plus $55 per day. Okay, everybody follow that okay? Hopefully you were all on that track.